Welcome back once again to our Chem 152 video series. In this video, we'll be talking about boiling point elevation. This problem says 30 grams of an unknown substance are dissolved in 100 milliliters of ethanol. We are given the density of ethanol, the boiling point constant of ethanol, and the boiling point of pure ethanol. We are also told that we have a new boiling point once we combine the solution together, and our goal is to find the molar mass of the unknown substance, assuming that it's a non-electrolyte. Let's begin by remembering what molar mass is. We're used to looking this up on the periodic table, but at its core, molar mass, or abbreviated mm, is equal to grams divided by moles. You may notice in the very first line, we are already told the number of grams, 30.0, and so we actually already know the grams, and so our goal is going to be to get moles so that we may calculate the molar mass. To do this, we'll use the boiling point information that we've been given. Now, seeing as how our boiling point began at 78.40 but has changed to 79.40, this means our boiling point has gone up when we mixed the solution, and so we need to think about boiling point elevation. The boiling point elevation formula says this. The boiling point of the solution is equal to the boiling point of the solvent plus I times Kb times lowercase m. Again, we'll go over what all of these symbols mean. So when I say T solution, I mean boiling point, specifically for the solution. T solvent stands for the boiling point of the pure solvent. The I, if you watched the video about freezing point depression, you would know that I stands for the Van't Hoff factor. And in Chem 152, we can think of this as the number of ions in the solute. Kb is the boiling point elevation constant. And lowercase m, as we've seen before, stands for molality. And let's recall that molality, lowercase m, stands for moles of solute divided by kilograms of solvent. Let's briefly take inventory and look at how many of these we know. The boiling point of the solution is given in the next to last line, 79.40. We'll write that down. We'll place a check mark next to it to show that we know it. We also know that the boiling point of pure ethanol is 78.40, and that's the T solvent. We'll check that off as well. Now I, the Van't Hoff factor, is not given directly in the problem, but the problem does say that this is a non-electrolyte, and any solute that is a non-electrolyte automatically has a Van't Hoff factor of exactly 1. We'll write down that I equals 1, and so we also know I. The boiling point constant, Kb, is also given to us in the problem, and it's 1.22. Check that off as well. So press pause for a second, and you may realize that we know almost everything in this formula, but the only thing we don't know is the molality. For the moment, I'm going to write that molality is an unknown. Now, we don't know what the molality is, but we do know that molality is the same thing as saying moles of solute over kilograms of solvent. So what we're going to do is modify this formula and place this fraction, moles divided by kilograms, in place of m and see if that makes a difference. Here I've rewritten the little m as moles of solute over kilograms of solvent. The orange box that I'm drawing now is where molality used to be. Now, we don't know the moles of solute, but we have the chance to get the kilograms of solvent, because we have some information about the solvent in this problem. At the end of the first line, we are told that we have 100 milliliters of ethanol, and we're also told the density of ethanol. So in order to get the kilograms of solvent, we can use the 100 milliliters, along with the fact that we know the density, to help us get kilograms. So now we can convert the milliliters of ethanol into grams of ethanol. The reason I say grams is because the units given in the density involve grams and milliliters. So we'll go milliliters to grams, and then grams to kilograms. We have yet another two-step conversion. Now you're going to be tempted to start with the density. Again, like I've said before in previous videos, I advise against that. You want to instead start with your milliliters of ethanol, which were 100. We will get out of milliliters and into grams using the density. The density that we have is 0.789 grams per ml, so we'll place 0.789 next to grams and 1 next to ml. Then we'll multiply by another fraction to take us out of grams and into kilograms. Our SI conversions tell us that 1 kilogram is the same as 1,000 grams, and now we can do these operations in the calculator, where we take 100, multiply 0.789, divide by 1,000. If you place these in the calculator, you'll get 0.0789 kilograms. This will be our kilograms of solvent, and we will now place this in the bottom position in this fraction. We will now also check off the bottom of the fraction, meaning that the only thing that we don't know is now the moles. Now that we've collected all the information we need, let's place our numbers into the equation. The boiling point of the solution was 79.40. The boiling point of the solvent was 78.40, plus I, which was 1, times Kb, which is 1.22, times the moles that we don't know, divided by our kilograms of solvent, which were 0.0789. To deal with the algebra in this problem, it may be easier to subtract 78.40 from both sides before we go any further. This will cancel out the 78.40, and then we'll subtract on the left side and get 1.00 equals 1.22 times moles. And for clarity, we'll move this 0.0789 underneath the 1.22. Now, it may be simpler here to simplify this fraction down to a decimal number. And so divide this in your calculator. 1.22 divided by 0.0789. When we divide, we'll get 15.46 multiplied by our moles that we still don't know is equal to 1.00. Now we can divide by 15.46 on both sides. This will get our moles by itself. So we'll have that moles are equal to 1 divided by 15.46. We'll take 1 divided by 15.46 in the calculator, and we'll get 0.0647 moles. Now let's revisit the equation we started with at the very beginning. We said molar mass was equal to grams over moles, and now, after quite a bit of algebra, we've got our moles, and that'll go in the bottom position. If we go back to the very beginning of the problem, notice in the first line I've boxed in 30 grams. That's going to go on top. And on the bottom we place 0.0647, and now for our final step we divide. When we divide, we will get 463.8 grams per mole. If you want to round this to 3 significant figures, you will have 464 grams per mole. This will be the molar mass of your unknown substance. You can see it takes quite a bit of algebra to find molar mass based on boiling point, It is a long process, but it is possible. Thank you for watching. We'll see you again soon.